In Chapter 5, we take a new direction. We've spent all semester almost learning about the derivative. We first called it the rate of change, instantaneous rate of change. It's a limit of average rates of change. It's a slope of a tangent line. It's a limit of slopes of secant lines. We've looked at it from all different directions. We've looked graphically. We've learned all these shortcut rules, etc., etc. And now we want to turn our brains sort of inside out and say, okay, instead of finding the derivative of a function, now I want to find this thing called the antiderivative, which, by the way, I will abbreviate AD. So instead of being given a function f and saying, find the derivative, now we want to find the antiderivative, which is what it probably sounds like to you, going sort of backwards in the other direction. What function had this as its derivative? So, for example, suppose my little f function is x squared. And by the way, it's pretty standard calculus notation, if your given function is little f, to use a cap f for the antiderivative. And so my question then, in trying to find the antiderivative, cap f, is what function has x squared as its derivative? That's what I'm trying to figure out. So I'm not taking the derivative of x squared. I'm saying, what function can I take the derivative of so that my answer is x squared? So hopefully immediately you can start thinking, well, it must be a cubic, right? It must have a power of 3 so that when I take the derivative of something cubed, then I will get something squared. So we could try, for example, just x cubed. And as the definition says, cap f prime, so if I take this cap f and find its derivative, 3x squared, that's supposed to equal the little f that I started with. And that's not quite it. I have to divide out the 3. So if I use x cubed as my antiderivative, it doesn't quite work, because when I take the derivative of that, I get 3x squared, and I'm supposed to just get x squared. So if I divide by 3, then my cap f is x cubed over 3. Now I can check it. As the definition says, if I take the derivative of the cap f, I should get the little f. So I can take the derivative on the numerator, 3x squared, and the division by 3, I can think of that as multiplying by 1/3. Constant multiples get carried along, and the 3's cancel, and indeed, I get x squared. That's my little f that I started with. So that worked. So that's kind of where we're at. We want to try to think about what function has this that I'm given as its derivative. We want to find an antiderivative. Now, there's also this theorem that says if cap f is an antiderivative of little f, then the most general antiderivative is cap f plus c, where c is an arbitrary constant. So here they have a picture of members of what we call the family of antiderivatives. We have antiderivative, uncle derivative, lots of little derivative cousins, right? The family of antiderivatives, and you notice they all differ by a constant that has the effect of shifting the graph up or down. But you notice, for example, if we start at the very top with this black curve, y equals x cubed over 3 plus 3. If I take the derivative, y prime, I get 3x squared over 3 plus the derivative of the added constant 3 is 0, and of course the 3's cancel and I get x squared back. And if I look at the orange curve, which took x cubed over 3 and shifted it up 2, and I take the derivative of that function, oh yeah, I'm just going to get x squared again. And if I look at the blue curve and I take its derivative, once again, I get x squared. And so for all of these that differ by a constant, their derivatives are all the same because the derivative of the added constant is always 0. So these all have derivative x squared. They are all antiderivatives of x squared. So in general, we could have said up above, because the question said find, well, I guess I didn't write it explicitly. I think I said it, find n antiderivative. But we can say the general antiderivative is cap f of x equals x cubed over 3 plus any constant c that I want.